So last time, I explained, again, as you know, in this chapter, I'm explaining AC circuits. Everything we have done so far in this course before this chapter, it was DC circuits. Okay? In DC circuits, the sources you have, either current sources or voltage sources, are actually DC. And DC means the amount of current, the amount of voltage are constant over the time. Okay? But here, actually, the voltage or current are sinusoidal. Okay? In the coming chapter, the next chapter, it will be continuation to this chapter. In this chapter, I focus on how can you calculate the total impedance or equivalent impedance. Also here in this chapter, I focus on how can you calculate the current and voltage. But I did not talk at all about power here. How can you calculate power? And this is the topic of the next chapter. So next chapter is going to be, I'm going to explain how can you calculate the power in case of AC circuits. Okay? Anyway, so last time I explained this circuit here. How can you calculate Thevenin for this circuit? Okay, and so here after you calculate Thevenin to this part, you need to find V Thevenin and Z Thevenin. Okay, and you can see here this is exactly similar to what we did before, but here everything is a complex domain as I told you. Okay, I told you in the coming test there will be a question, will be very close to this example or next example here. I will give you a circuit. I will ask you to draw or to find the Thevenin of this circuit, similar to this one here or this one. Okay? I did not explain this one last time, so I will start from here. So here in this, I think it's the same example. Yeah, you have here RS, you have Z1 and Z2. So I give you Z1, okay? I give you Z2. Z2 is negative J, okay? Can anyone tell me when you find negative J, is this a capacitor or inductor? Or you can't know? If I just tell you negative something J, you can tell if it is inductor or capacitor or you don't know? Yes, it is a capacitor. Because in case of a capacitor, it should be 1 over J omega C. Okay? 1 over J is actually negative J. Okay? So, and when you find the real part, like this one, this is a resistance, and this one here is inductance. Anyway, so I give you here. I think there's a mistake here. This should not be VS. No, sorry, this is VS. This is for this one here. So I want to calculate Norton for this part. Okay. So after you calculate Norton for this part, similar to what we did before, you are going to have an impedance here instead of resistance. Before we said it should be resistant. In this chapter, we should have impedance here, and I should have a current source here. So all what I need to calculate is actually Z Norton. Also, I need to calculate I Norton. Okay. So to do that, I will do exactly the same thing as we did before. So the way we can do it here, as you see, number one, if you want to calculate, because this is a circuit in here, so I have to cut here as we did before. Okay. Number one, if you want to calculate Z Norton, so I need to find the impedance here. Okay, I can. For sure, this one is EC, so voltage source has to be a short circuit, and then I need to find the total impedance if you look from here. If you look from here, can anybody tell me what is the total impedance if you look from here? Z1 and Z2 are series or parallel or none? None. They are parallel. So all what you have to do is actually the total impedance is actually Z1 is in parallel to Z2. Okay, and that's what I did here. Very easy. Yeah, so here as you see, Zn should equal Z1 in parallel to Z2, which is actually Z1 times Z2 divided by Z1 plus Z2. Just you need to do this calculation with a complex domain. After that, this is the result here in the rectangular form, and this is the result in polar form. Okay. Now, how can you calculate I Norton as we did before? After here, I cut the circuit here. You need to add a short circuit here. Okay, you need to make a short circuit, and then you need to find the current in the short circuit. should equal to I Norton. Okay, so I need to find what is current here. Okay? As we did it many times before, if you have a short circuit over a resistance or impedance, okay, what should happen? You cancel the impedance. So one student asked me about this one. He was not somehow very convinced about it. So anyway, so actually, you know, if you have here R1 and you have R2, if you want to get the total impedance here, it has to be R1 times R2 divided by R1 plus R2. Okay. So imagine if one of them, like for example here, R2 is actually short circuit. Short circuit means the resistance is 0 ohm. So if you just plug in here, you can find 0 times R1 divided by R1 plus 0, which is actually equal 0. If you like it to understand this way, that's okay. There is another way to explain it, as I told you. In general, if you have two resistors, for example, here you have R1 and you have R2, okay? As here, if I have a current here, I, okay, so this current actually divided between R1 and R2. It will not be, if R1 is equal to R2, it is divided equally. But more current is going to go to the smaller resistance. So what happens here, as I make this resistance smaller, so actually more current is going to come here and the less come here because the summation is fixed. The summation of the two currents are actually odd. So when I reach to the point that it's 0, nothing will come here because this is an easy path. All the current will come. Anyway, that's another way to explain it if you like this one. So again, if you have, that's what I want to say, if you have a resistance or impedance, okay, and there is a short circuit, okay, so actually you cancel this one because no current, so everything will come here. You can see, you can explain it in different ways. One of the ways is, you see, you know, if you have a resistance, there is a voltage drop. When you have a current, you have a voltage drop. You got what I'm saying? But here, because this is a short circuit, the voltage drop here is 0, right? So the voltage drop here is also 0. There is no voltage drop. You got what I'm saying? But anyway, yeah, so as you see here, yes, this short circuit is against this one. So it's like this one does not exist. Can you calculate the current? So all the current will come from here through this circuit. This one, you can just remove it. Okay? So actually, it's very clear here. This current is actually Vs divided by Z2. Okay? And this is EC current. Okay, EC current. And we calculate it. So as you see here, I Norton should equal Vs divided by Z2. This one, because this one cancels. So actually, yeah, this is Vs is here. Z2 is here, and you can calculate it. Okay, that's it. Once you have, once you have IN, ZN, okay, this is a circuit. So this circuit actually is equivalent to this circuit after using Norton. Any questions? Again, nothing is new. That's exactly similar to what we did before, but all the calculations are done using complex numbers. Okay. I didn't ask you or to translate it to time domain. Okay. So just I want you to draw the circuit here in complex domain, and that's it. Any questions? Okay. So here I think we have how many examples here? 13. Yeah, we have multiple examples here. 1, 2, I think 3 examples. Okay. So let's move to the next one here. Okay. So same thing here. I want to calculate Thevenin and Norton equivalent to this circuit here. Okay, guys. Again, this is a mistake many students did in test number 1. Try to remember. If you have a dependent source, like this one, you cannot calculate resistance similar to what I did here. Here, as you see, I can calculate the resistance this way, either to Norton or Thevenin, because we don't have here and it's a circuit does not have a dependent source. So I can do it this way. Okay. So now, because you have a dependent source, the only way to calculate this impedance is I need to find V Thevenin, as you see here. So number 1, I need to find V Thevenin. I need to find I Norton. Okay, and Z Thevenin and Z Norton are equal. It's easy. So these two are equal. So I need to find only one value, which is actually V Thevenin divided by I Norton. You got what I'm saying? So all what you have to do is you need to find V Thevenin and I Norton. That's it. After that, you can calculate these two resistors because they are equal, V7 divided by I load. Okay? Again, you must use this approach. You cannot use this approach because you have a dependent source. Okay? Any questions? Okay. Let's see how can we calculate this V7 in here. And also there is a small trick here I want you to learn. Okay? So for this source, for this dependent source, it's a voltage source, as you see here. And the voltage source is actually 3 times V. And V is the voltage here. So the value of the voltage here of this voltage source is actually 3 times V. V is the voltage drop here across R. Okay? So now, again, similar to what we always do, if you want to calculate V Thevenin, you have to open the circuit here. As I did here, you have to open the circuit, and then I need to find the voltage drop here. Is that okay? So let's see how can you calculate the voltage drop here. Okay. So first of all, and there is a small trick here I want you to learn. Very important. Okay? So here, guys, look here. Number one, IS, I have already IS, I have R. Both of them are given to me. Okay. Let me ask you a question. This current here, where this current is going to go? It's going to go, all this current is going to go through R. Nothing will come here. Why? Because there is no path. There is no path here. That's too simple, right? So all this current will come here. That means can you calculate V? Yeah, for sure. V is actually equal IS times R because all this current will come here. Yes, and that's what I did. So when I calculate it here, that's what I mean. IR equal to IS, and then I multiply R times IS. Okay, so this is the voltage V, the voltage here. Okay, guys, any questions? So this actually give you the voltage here. I want to calculate the voltage at this point here, V7. Okay, this is some. I'm sure most of you will be confused here. Okay, someone can say, and that's wrong. Someone can say because the current here is equal to 0, so the voltage here equal to the voltage here. Similar to what we did here. So if you see, yeah, this example, once I find the voltage here, okay, I said because there's no current in this impedance, the voltage here equal to this voltage. That's what I did here. Okay, but there is a big difference between this one and the previous one. Okay, the difference is in case of impedance or case of resistance, it's true. So if you have here, for example, if you have something like that here, and then you have here a resistor this way. Okay, so if the voltage here is V, also here it's V. Why? Because the drop here, the voltage drop is 0. Why is the voltage drop is 0? Because the current is 0. There is no current here. Is that okay? And in order to have a voltage drop in a resistance or an impedance, in order to have a voltage drop, there should be current. There should be current. Okay? No current, no voltage drop. Very simple. Okay? However, this is not the case if you have a voltage source. If you have a voltage source, instead you have a voltage drop, even if there is no current. You understand what I'm saying? So here, if I have a battery, this battery is 5 volts. So even if there is no current here, okay, still, even if you open the circuit this way, the voltage drop here is still 5. Big difference. Okay, that's why if you have here a source, and this is actually our case, this source, for example, 5 volt, for example. Okay, if you have a source here, so actually, and here this is a positive, negative. Okay. So actually, I want to calculate the voltage here. The voltage here, okay, here the voltage is V, but the voltage here should be V plus 5, and here V plus 5. Why? Because there is no drop in the resistance here because there is no current. But still, because you have a source here, still there is a voltage drop even if there is no current. Okay? Because the resistance is different from a source. Okay? And that's exactly what I did here. So what I did here in this example, I just want to bring this one to your attention because this example is different from the previous example because we have here a source here. Okay? So after I calculated V here, so actually the voltage of this point is V. Okay? So the output voltage here should be actually V, and then we have another 3 voltage here drop. So the output here should be 4V. So this one is V, and we have 3 here. So this point should be 4 V. Okay, and we already calculated V. So what you have to do, I have as you see here, should be 3V plus V, okay, which is 4V plus 0. But you are going to drop across this impedance is 0. That's it. Okay, guys? Yeah, sure.
But the 3 volts going from negative to positive, is that still a positive 3 volts, and you don't subtract the 3 volts?
Yeah, so this is not 3 volt. This is 3 times V.
Oh.
Okay, this is 3 times V. This is not, yeah. So this is 3 times V, and this is V here. You got what I'm saying? This is not 3 volt. This is 3 times V, and V is 0. Regarding your question, should I add or subtract? This is very simple. Look here. If you have here positive and negative this way, look here. What this means, for example, when I say this one is 10 volt, what it means? It means the positive side has to be greater than the negative side by 10 volt. Okay? So that's why if I tell you, if I have here 20, so this one should be 10. Okay? If I have here 10, so this one should be 20. If I have 2, so this one should be 12. So always the positive side has to be greater than the negative. Okay? So that's why if you have here, if I have the voltage here, I call it A. So to move from here to here, this one has to be greater. So it has to be A plus 10. But if I have this one B, and I want to move from here to here, so actually this one should be B minus 10. Okay, don't be confused. After you calculating, you need to look at the voltage at the positive side and negative side. If the positive side has to be greater, otherwise you did it wrong. Okay? Anyway, so now that's it. After that, I found V7. So this is V7 here, and this is AC source. Okay? I said it before, if the angle is 0, doesn't mean this is DC. This is the angle. Still, you have cosine omega t plus 0. So it's cosine omega t, still AC. Okay? Anyway, let's move to now. What should I find? I find now, I need to find I Norton. How can you find I Norton? I have to make a short circuit this way. Are you okay with that? I can make a short circuit this way. And then the current here is I Norton. That's what I did. So here, now, as you see here, I made a short circuit this way, and I wanna find the current here. Okay. The mistake that I found in the first test is I wanna find V. Some students just use the same value of V you calculated here. That's wrong. This circuit is not like this circuit. You got what I'm saying? Because of this short circuit, this circuit will be different. Some students, the first stage, just they took the value calculated in V here and just they used it here. So it's wrong. These are two completely different circuits because I made changes. I changed it, right? By adding this one, by adding the short circuit here. Anyway, so now I want to find what current you have. You can see this voltage source and also they are in series. So this current it should be the same current, has to go this way. Okay? So whatever the way you want to use it, you can. Once you find the current here, it will be the same current like this. Okay, let's see how we can do it. First of all, here I can use, maybe you can use nodal if you solve it using voltage node. You have only one node to solve. Also, if you want to use mesh, also should be easy. Why should be easy in mesh? Because if I1 here is equal to IS, you see, so I1 here. I1 equal to IS, okay? So this is the first thing here, I1 equal to IS. Number 2, V here is actually equals to I1 minus I2 times R, as you see here. I don't know, my unknowns, and you know, in case of mesh approach, mesh analysis, the unknowns are I1 and I2, okay? So now I already know I1. I1 is already known, which is good. Because I need to find I1 and I2. I already done with I1. I only need I2. You get what I'm saying? So that's why I'm saying here mesh is not bad. Although still, I think still voltage node is easier. You will see as I can explain now. But also it's not bad here because you don't need you are gonna have only one equation with one unknown. Why? Because I already have I1. Okay, so that's why it's not bad here. Anyway, so I already have here I1. Okay, and now I know the V is actually I1 minus I2. Anyway, so now I can apply Kirchhoff voltage here in this part. So if I or in this part here, you can see should be here negative 3 volt, as you see here, okay, times I2 times Z, as you see here. And actually, here, this is the important part because V, this is the positive of V, this is the negative. So when you come here this way, so actually it has to be negative V, not positive V. Okay, maybe I'm sure many students will be confused here. If I tell you the voltage here is V and this is the positive V and this is the negative, in case of I1, so it's gonna be actually here in this loop, V, I'm gonna take it positive, but in this one here, because the current from negative to positive this way, okay, because this is already, I tell you what, this is V, so this way you have to make it minus. Anyway, so once you have this equation, not only one unknown. Look here in this equation, actually you have, look at this equation, you have two unknowns, which is I2 and V, right? But actually V is already I know I1, okay? So here V is already functioning I2. So this equation actually is gonna be functioning only I2. So here I plug in here the value of V from here, and I know I1, okay? So now this equation has only I2, and then I can solve it. And that's it, because I short circuit here is actually I2. Okay. By the way, still I think it's easier to use voltage. I think it's easier to use let me see here. I want to show you. I want to solve it. If you use voltage analysis, I think it will be easier. Let me see why it's not working. But anyway, so what I can do here. So anyway, I will explain it from look here, guys. So now, what is the voltage here? The voltage here is V, right? Okay. So if I have only one unknown, which is V, only one unknown, which is V. Okay? So actually, you can apply Kirchhoff current law. So here's the input here, IS. I already know IS. Okay. And now, here's the current here, IS should equal to the current here, which is V divided by R. V divided by R for the current here. For this current here, the current here is actually, this one is V. So this one actually 4V. This one is V, so this one should be 4V. And now the voltage across Z is actually 4V minus 0 divided by Z. So now I have an equation that has only one unknown, which is V. Okay? Let me say it again. Look here, guys. When I use the voltage analysis, I have this voltage here is V. This is the only unknown I have, only one unknown. Okay? So here, input current IS, I know it. The current here is actually V divided by R. I know R, I don't know V. Okay? The current here, because this one is V, and this one should be 4V. Okay, so the current here is actually 4V minus 0 divided by Z. Okay? You have everything except V. Once you get V, you can actually easily calculate I Norton, because I Norton here is actually 4V divided by 0 over Z. Anyway, this is another way to do it. Any questions? Once you have I Norton and you are done. So now I calculated. Now I can calculate Z Thevenin or Z Norton, which is actually V Thevenin divided by I Norton. You can see all the numbers here are complex numbers. Okay? And then after that, I can, okay, so now I know V Thevenin, I know I Norton, Z Thevenin equal to Z Norton. Okay, now I can make the two separate this way and I know it. Any questions? Okay. Okay. So we have two more examples. Okay. So the next example here, guys. Again, I'm gonna use op-amp. And by the way, I want to tell you something I noticed when I graded the previous test. Really, even in the lecture, I told you should not do this one. Okay. So remember in the previous test, you have here negative. Let me remember, you have a resistance here, you have here V out, and then you have a resistance here, and then you have ground. Also, you have here I think it was a current source. I'm gonna call it R1, I'm gonna call it R2, and then I'm gonna call this one IS, whatever, okay? We agree, the current here is equal to 0. So there is no current here. Makes sense? That's what I agree. That means the current here IS, so the current here should actually equal IS plus 0. Makes sense? And this is the way you have to solve it. I have to say input current IS should equal to 0 plus the current here, which is actually 0. Sorry, whatever the voltage here. I don't remember. So whatever voltage here, I'm going to call it V. So whatever this voltage equal to this one, it has to be V minus V out divided by R. Voltage drop divided by R. Is that okay? This is the way you have to do it. The mistake some student did, and really this is not a good mistake, is some student instead of working on IS and R1, they worked on R1 and R2. Okay, so what they did, they said this is V. And this current here, okay, I'm going to call it I1, is equal to I2. Okay? So here, I1 equal to I2. And I1, actually, V minus V output divided by R1 should equal to V output minus 0 divided by R2. What's wrong here? What's wrong? I didn't say this current is 0. You assumed that. I didn't say that. You got what I'm saying? So if the current here is 0, yes, what you did is correct, but this current is not 0. And I don't have a way to calculate it. So if I want to calculate this current, I need actually to calculate I1 first, and then I calculate I2, and then I apply Kirchhoff current law to calculate this current. But there is a current here. You got what I'm saying? So it is true to do it here, to say this current equal to this current. It is not true to do it here because this current is not 0. This current's input to the op-amps are 0. Okay, I found some students this mistake. Okay? Anyway, so here I'm gonna show you. We have here in this example, we have an op-amp, okay, similar to what we did before, but here we have EC. The input is EC. Also, we have here capacitor and the resistance here. Okay. So you will see right now the way I will analyze this circuit exactly similar to what I did before. However, I'm gonna replace this part by impedance. I call it Z. So now it becomes like you have here normal op-amp. Then here we have an impedance. I'm gonna call it Z. Then we have here resistance, and then we have resistance, whatever. Okay, it's gonna become okay. This one, we are very familiar with this one. Okay, you already know what is the formula for this one, by the way. So you already know V output divided by V input should equal minus Z divided by R. Okay, yeah. Or you can derive it. You can derive it by assuming, as you will see right now in this example. So let's see in this example here, guys. I give you this circuit here. I give you here. I wanna find V output divided by V input. Okay. So number one, you need to calculate this impedance here, which is capacitor in parallel with R2, as you see here. So I already calculate this impedance, okay? And that's what we are doing with this chapter. Every impedance, you deal with every impedance like a resistance, like similar to resistance as we did before. Okay. So actually, in this example, you don't even need to drive it because we're already familiar with this circuit. This is an inverting amplifier. And V output divided by V, which is equal negative Z divided by R1. Okay? But I will derive it. So here, the way I have to drive it, as we did before, is you know this current here, this voltage is 0, right? So this one is equal also to 0. This one is 0, so this one V1 is 0. Okay, as you see here. Also, this current here equal to this current here. Okay, so this current is actually Vs minus 0 divided by R1. Okay, this one should equal to V1 minus V out divided by Z, because this current is 0. That's it. So if you do this way, you can now get the ratio between V out divided by Vs, which is equal to negative Z divided by R1, and that's what we did before in inverting amplifier. Okay, but this one was Rn divided by R1, or R2 divided by R1. So here I calculated it, it's the same way because this impedance is like resistance. Okay, guys? And then after that, here, Z actually, is equal to R2 in parallel to 1 over G omega C. Now I got this formula. Yeah, so it is Z divided by R1. Z is actually, this is Z, okay, which is R2 divided in parallel to G omega C, okay, and then this is the result I have. I think in the second part of the question, it's very easy. So this is a relation between input and output. So if I give you input, you can easily calculate the output, and that's what I did. So what I did in the second part, I give you numbers, okay? In the first part, I didn't give you numbers. I need a formula, and then I found the formula this way. Again, there is no, I didn't teach a new circuit here, okay? I just used everything we learned it before, okay? So here, I give you R1, I give you R2, I give you C, I give you the input here, Vs, this is the input here, okay? And then you can just plug in here, because this one here gives you the relation between V out and Vs. You already have Vs, I give you R1, R2, I give you omega, I give you C, I give you R2. You can just plug in, but this way you can, number one, you can find the gain. So the gain here is a complex number, as you see here. And then after you find the gain, okay, you can, I ask you to calculate V output. So V output should equal gain times Vs. You already have the gain here, which is this one here. And you have Vs, this value for Vs, you can multiply and then you can find V output. Once you have V output in the complex domain, it's easy to convert it to the time domain. The same amplitude here equal to maximum value here, omega t, don't forget to add omega t, and this is the angle. That's it. So for this circuit, this is the output you will see. If the input is 8 cosine omega t minus 60, the output is 25 cosine omega t plus 44. So you change two things. You change the angle, right? Because you have a capacitor. You know, if you don't have a capacitor or an inductor, you don't change the angle. It will be the same angle. Resistor does not change the angle. What I'm saying? Because we have a capacitor here, we change the angle, also change the amplitude. Amplitude here was 8, now it became 25. Angle was negative 60, now it's 44. Okay? Yes.
The previous slide, why is it V0 minus Vs? Because you're saying IR1 is going this way. So shouldn't it be negative to show that it's going out?
I know what confusing you. So what you are confusing you here, this one here has to be Vs minus V1, right? Vs minus V1 divided by R1. Is that okay? Should equal to output. Output here is 0 plus V1 minus V out, okay? So if you bring this one to the other side, it will be okay. It's like I moved it. You get what I'm saying?
But if you're assuming the current is going this way, shouldn't you keep it at the same? Or
that's what I'm assuming it's going this way.
So shouldn't it be?
I moved it. So this current,
okay.
This current has be Vs minus V1 divided by R1 equal to V1 minus V output divided by Z. And then I moved it. That's why when I moved it, it became V1 minus Vs. You get what I'm saying? Okay. Now I will come to the last example you have here, guys. I made it very clear, guys. When I analyze these circuits, I have to make sure omega, we are only use one omega. You got one value for omega. Because by changing omega, you change the circuit. Okay, by changing omega, impedance it changes. Okay, all impedance changes, so change the circuit. Okay. Even in the calculation, I delete omega, I don't use omega. What I'm saying? Because all the maps is in omega. So now this example is very close to one example I explained before. When I have two sources, one, let me go back. Just I want to connect. This example is very similar. I will show you what is the difference. Very similar to an example we had before when we had AC and DC, because you can see. Okay, let me go to the example first. Not this one. Yeah, I think not this one. What was the example we have? Yeah, this one here. So here in this example, guys, remember what I did? This one we have two sources. This one has omega, which is 10. This one is DC, not AC. You can see, you can consider DC is like AC with omega is equal to 0, frequency is 0. You get what I'm saying? So now I have two circuits with two different frequencies. I can say that. What I'm saying? So that's why this example is very close to the example I'm going to explain right now. But here omega is equal to 0 because this one is DC. In DC you can see DC like AC, but frequency is equal to 0. But in the example I will explain right now, I have two sources with two different frequencies. You get what I'm saying? Again, when you solve everything we do so far, we have only one omega, one value for omega. Okay. So now if you have two sources with two different frequencies, what you can do is you can do superposition. Keep one source so that the whole circuit will have only one omega, remove the other one, and then repeat again. So again, you need to keep in mind everything we did so far in this chapter is all the circuit should have one omega. So in case of you have two sources with two different omegas, okay, so in this case you can actually separate them. Okay, that's what exactly in this example is about. So this example here, yeah. So in this example here, you actually have two sources, one voltage source and one current source, as you see here. Okay, the voltage source is actually omega here is 5. I don't care about the angle. If the angle is different, I don't care. If the amplitude is different, I don't care. The problem here, because omega is different, okay? So here we have current source and voltage source as you see, but they have different omega, okay? So so the best way to solve this problem here, I need to find I. Where is I? Yeah, I need to find the current here I, okay? So the best way to solve this is just using superposition. In superposition, I'm going to have, instead of solving one circuit, which is actually I can't solve because it has two different omega, I can solve two different circuits, okay? One with one source, the other one with the other source, as you see here. So when I keep the voltage source, I'm gonna make the current source open circuit, as you see here. Okay? In the next circuit, when I keep the current source, I have to make the voltage source short circuit. We always do that, right? In superposition. In superposition, any voltage source you have to make short circuit, any current source you have to make it open circuit. So now it became easy. Now I have to solve this circuit. I need to find I1. I need to solve this circuit to find I2, and then I will add I1 plus I2 to give me the total current here I. At least now we have two circuits. Every circuit has only one omega. That's exactly what I want. Okay? So let's start. Let's start because that's very easy. So now because I need to find this I here, guys. I want to find this I here. To find this I need to find I1 and I need to find I2, and then I have to add them together. Okay? How can you find I1 in this circuit? That's very trivial. All what you have to do, you have to divide VS1 by the summation by the total impedance. The total impedance is actually R plus J omega 1L, as you see. Okay? So here to find I1, as you see here, I just divide VS1 by actually R plus J omega 1L, as you see here. I have everything, I can calculate it. Once I calculate it, I can convert it to the time domain. So this is I1. So this is the current, this is I1 in time domain, because this is the time because of this source. This is the impact of this source, okay? Also, this is a contribution of this source, okay? Now, let's do this one here. So you have here current source, and you have impedance here, and you also have impedance here. Can anyone tell me how I can calculate the current here? This current here. This impedance R and the inductor here, they are in series or parallel? They are parallel. So actually you can redraw this circuit this way. So this circuit you can redraw it. So here you have resistance, you have here a current source this way, and then you have here an impedance this way. So I can redraw this circuit this way. You have here current source, and actually because they are in parallel to each other, R and Z. So yeah, all of them are in parallel. Why? Because this point is shared for all of them, and this point is shared for all of them. They are in parallel. Okay. So that means if I want to calculate, the current here in R. Okay. So to do that, the way you have the easiest way to do it is using current division. So current division here, if I want to calculate this current here, should be I total, which is this I here, okay, times the other resistance impedance divided by the summation of both of them. Okay, this is one way to do it. There is another way. You can get here Z equivalent. Maybe this is for sure. Current is easier. Okay. So Z equivalent is equal to R in parallel with Z, and then you can multiply I times Z equivalent. This should give you V. V is the voltage drop here. Okay? Once you have the voltage drop, you can easily calculate I1. So I1 here equal V divided by R. You can also calculate I2, which is actually V. You can also calculate I2, which is actually V divided by Z. Okay, I think this one is easy. By the way, also I find something very weird in or some student made this mistake, guys. In exams, you have to be careful when you apply current division or voltage division, guys. Okay, you have to be very careful. When I explained it, I was very clear. I said, if you have here R1 and you have here R2, okay, and then you have total current here I. So this is the case you can apply a current division. A current division. Same thing for voltage division. If you have here R1, R2 in series, and you already know the voltage here to across all of them, you can apply it here. I found in the exam, let me remember the exact case, but what happened, this we have R1, we have here R2. I think I'm trying to remember, but some student made this mistake, and then I think you have a capacitor here this way, and then some student applied current division here between this part. You should not ignore. So this one is not equivalent to this one here because you have another branch here. You got what I'm saying? So it's just you applied it here. This one is not like this one. You have to be careful. You got what I'm saying? Same thing in the previous chapter when we had equation. Remember when we had equation, we got equations for a very specific case when you have R and C. So if your circuit is different, it's something else, you have to make it this way. You got what I'm saying? So when you have a switch. Okay. So anyway, yeah. So here I can apply. I think here I can. Yeah, I applied the current division here. So I applied current division. I multiplied IS2 times this impedance divided by the summation of two impedance. Okay. But here you have to make it negative. Why negative? Because actually this current will come here and then it's gonna go this way and it's gonna come to this way. So the current here actually is gonna be the opposite of this one. Okay, that's why I made it negative. Because or so the current here has to be in this way because it's gonna be distributed from this source direction of this source. Anyway, after that I just did the calculation. I calculated I2 as you see here, and then you have I1, you have I2, you can add them together. You can see here, this one has omega t of 5, which is the same like the source. The source here is 1, it was also 5. Okay, here the omega is 10 because the other source was 10. When you add both of them together, for sure you cannot add them because one component, as you see here, when I add them together, one component omega is 5. The second component omega is 10. You got what I'm saying? Any questions? Okay. Now I want to move to the last part here in this chapter. Okay. Yeah. So before I move to this part, I want to because we are going to extend what we did regarding inductors. Okay. So I'm going to very quick revision on inductors. Because we have inductors and we have something else where we have coupled inductors. or coupled. Coupled means connected, coupled inductors. There are some similarities and differences, but you need to understand they are somehow different. So you will see right now what I mean. Because this is something new. I did not teach you this one before, okay? What we have done so far in inductor, I told you if you have, this is what inductor is. You should have a core here. That's what I explained. This core is made of magnetic material, and then you need to make wire. So here you need to turn the wire across this magnetic material. If it is this way, that's what we call inductor. Okay, and you know there are very important two theorems in here. I'm sure you are familiar with it. Okay, so here you know, guys, if you have a wire and then you have a current, so actually there will be magnetic field here. So if you have any wire, and this wire has a current, you are creating magnetic field. Okay. And also, if you have a wire and they have magnetic field coming from somewhere, you are gonna actually have a voltage here. So two things here, okay? As you will understand the two things. Number one, I have inductor, and then there is a current flow through the inductor, okay? So the current flow through the inductor is going to make a magnetic field. This is number one. Number two, if I have a magnetic field coming from another inductor or whatever, and then I have a wire, this wire is going to have a voltage across it. Because that's what we call Faraday's law. Okay. Anyway, I will explain to you here. Okay. Anyway, so that's what I just want to show you what I want to explain. What is the difference between inductors we used to before and what we mean by coupled inductors? Okay, and how they are similar, how they are different. Okay. So here, as I told you, we have here only one coil. I turn this coil across a core, okay, of magnetic material. Okay. And as I told you before here, the voltage should equal L dI divided by dt. Is that okay? And what this equation is telling me? This equation is telling me I has to change over time. That's why if I does not change over time, the voltage is zero. What I'm saying, the voltage is zero. So it should be, that's why when I is DC, there is no change. That's why voltage is zero. That's why it short circuit. You understand what I'm saying? So there should be a change in the voltage, in the current, in order to get a voltage. Okay? There is another formula I did not explain, we didn't need it, but actually it's Faraday, we call it Faraday law. Okay? So, not Faraday. Yeah, Faraday law. So actually here, V also should equal N d phi by dt. Okay? Here I'm talking about inductors because I will come to coupled inductors. Okay? N is the number of terms, how many terms we have. Okay? d phi by dt is the change in the number of flux or change in the magnetic field. Okay, so here, because you should have, once you have here a core this way, and then you have here this way, there should be magnetic field here because of the current you have here. Okay, so phi is actually the number of flux, or it's related to the magnetic field. Okay. Anyway, but what we did so far, we use this one all the time. Okay. Anyway. So this is inductor. That's what I explained. Now I want to talk about something else. We'll call it coupled inductor. Okay. So what happens here is I'm gonna change number one. Instead of using only one coil, I can use multiple coils instead of usually these two, but you can use more if you want. Okay. And I will change how the core looks like. So actually, what I can do here is. I can have a coil this way. So this is the core. This is the core. This should be from magnetic material. So instead of it was like that in inductor, no, I will make it this way. And then I will tell you why. And then I can have here one inductor this way, and then I can have another inductor this way. Okay. And then here you can have a circuit. For example, I can make here a lamp. Yeah, I can put a lamp here, for example. Okay, a lamp. Here, I can put a voltage source here. Okay, but this voltage source has to change. Okay, because it does not. You can see even here, don't you guys? Because we have differentiation. So if this flux is constant, this one is zero as well. So it should be AC, not DC. Okay. Anyway, so again, there is no electrical connection here. Listen to me because that's very important. There is no electrical connection. So this circuit here, the current will come here, this one circuit. Okay, so this is a circuit. And then if I do that, if I connect, if I have a switch here, if I connect the switch, I will find the lamp turn on because there will be a current will flow here. If I disconnect the switch, if I open the circuit here, I will find the lamp is off. What it means? It means I'm connecting the two circuits together. The two circuits are connected together, but they are not connected using electrical wires. They are connected using magnetic field. That's what you should understand. Why? Because once there is a current here in this part, I find there is a voltage here. No current, no voltage here. They are connected. That's why I say coupled. Coupled means connected. But they are not connected using wire. Okay, they are connected by magnetic field, which means once I close this one here, the current is gonna flow, and this current will make a magnetic field. And this magnetic field, I told you we have two important things in electromagnetics. Very basic things, two things. Number one, if you have an inductor and there is a current in this inductor, the inductor is going to make magnetic field. That's number one. Rule number one. Rule number two, if you have a magnetic field and you have a wire, this wire is going to have a voltage. Okay? Coming from induced voltage coming from the magnetic field. But there is a condition. The magnetic field has to change. If it's constant, you are not, the voltage should be zero. Okay? Because this is d1 by dt. Anyway, so here, what happens here, guys, when I connect this circuit this way, current is gonna go through this way, and then this magnetic field, this coil here is gonna make a magnetic field. This magnetic field is gonna go through this wire, okay? And because you have a magnetic field here, which is varying, you have to vary over the time. So I will get a voltage here. I will get a voltage here. Okay? That's why we say these two circuits are connected or coupled magnetically, okay, by magnetic field. They are not connected electrically, but using the magnetic field. Okay? Any questions? Yeah, sure.
Would it work with the current source or
Either. It doesn't matter if it's voltage source or current. What really matters is the source, AC or DC. Because if the source is DC, you are not going to have any voltage here. But if it is AC, yes. Why? Simply have to look here. d phi by dt, di by dt. Simply, if you don't have a change in the magnetic field, as you see here, you are not going to have a voltage on this one. Okay, guys? Yes.
if you first close the switch, will it actually induce just a slight?
You are right. Thanks. So here, what he's saying is, in case of DC, just you will see this lamp will turn on just in a very short period of time. Since when you change in the beginning during the transit time, because there's a change in the current, there's a change in the magnetic field just with short time. After that, it's going to be there is no current because no change in phi. So there will be a change in the phi just at the time you connect the switch. Okay? But if you want this time to turn on, if you want to connect the switch, and usually we use here AC. You need to use AC. Okay. I'm sure, and actually, this coil here, we call it primary coil. This coil here, we call it secondary. primary and secondary. Okay. What's the name of this one here? I'm sure you're already familiar with this one. What's the name of this circuit here? Transformer. Okay. So transformer, this is the main idea of transformers. Okay. So the main idea of transformers is something exactly as I explained right now, or you can call it coupled. In general, you can call it coupled inductor. Inductors coupled, connected together using magnetic field. Okay. But in case of one of the application, or one of the main application is actually using transformers. So this is here into some transformers here. It looks something like that here. Here you have V1, here you have V2. Number of terms here, I'm gonna call it N1. Number of terms here, I'm gonna, it's actually, it may not be the same. So here number of terms, how many terms here is N1? How many terms here, I'm gonna call it N2. And then there is something very, very interesting now, okay, which is V1 divided by V2 should equal N1 divided by N2. And V1 is here, V2 is here. Can anybody know? I'm sure you should know how we use transformer. Have you, for sure, I'm sure you heard about transformers before. Why we use transformers? To do what? Yes?
Increase the voltage to carry it across the power line, and then decrease it to get it back into your.
That's correct. So in general, it is used to increase the voltage or decrease the voltage because of this formula here. Okay? So in this formula here, I can say V2 should equal to okay, N2 divided by N1 times V1. Okay. So as you see here, if the number of turns here is actually 100, that means the voltage here is actually 100 times this voltage. To step up the voltage. Or sometimes we need to step down, reduce the voltage. For example, if the ratio here, for example, half, if the ratio is half, so I'm going to have half voltage. Okay, so the voltage in V2 is actually half of V1. So sometimes I will give you very, as we explained, I will give you a specific application. But in general, transformers are used to increase the voltage or decrease the voltage. Okay, as we give you details. So this is example for coupled inductors. This inductor again is they are not connected using wires or electrical. Electrical is isolated. Electrical, but they are coupled, they are connected by the magnetic field, okay? The impact of the magnetic field. So the application that needs to increase the voltage or decrease the voltage is actually our power system. So in our power system, guys, what happens is that in the generation, we have transmission, and then we have distribution. Here is the consumer here. Consumer is here. Okay? In the generation, you actually, for example, you can generate 25 kilovolt. You can increase it to 100 or maybe more kilovolt. So I use transformer here, and then I will transmit the power in the transmission using very high voltage this way. For sure. It's too much, right? 100 kilovolt, right? In our homes here, what we use is 110 or 120. Okay? So here, what happens here, I need to step it down. That's why I use transformers. It's you can find it's everywhere. Sometimes it's very big transformer, and sometimes they need some cooling because they produce a lot of heat. Anyway, I need to reduce it to 110 or 120 volt. That's why I need to use transformer. And the reason we wanna it's better so someone can say why you don't even make it 110 volt and then transmit 110 volt from the generation to the distribution. Okay, the way or the reason I need the voltage to be too high here is actually to reduce the loss, because there is a lot of loss here in the wire. You lose a lot of energy in the wire. Okay, so don't think if I generate X power here or energy, I will receive X here because there is some loss here in the wire, and then I will talk about it in some details later. But the wire, there should be a loss. That's why it's better. That's why it's better to increase the voltage, and that's what we do. And then now we need to reduce it back. So to do that, we use transformers. Okay, You can see here around the building, you can see like 3 big transformers. Inside the electric circuits, you can find very small transformers. Sometimes they are small, sometimes big. You can see, but anyway, but all of them are doing the same thing actually. You can change the voltage. Okay, this is one way, or this is a main use of this idea. It's just to step up the voltage or step down the voltage. This is one thing. The other thing is sometimes I use them if I wanna, even if I don't want to increase or decrease the voltage, I wanna get the same voltage. Okay, I can use it. It's the same voltage. But the good thing here is that I want to separate 2 cells together for some reason. I have a circuit. I want to connect this circuit to this circuit, but I want them to be electrically separated. So that if damage happens in this circuit, it's not going to impact this other circuit. You get what I'm saying? So still I can use it. But again, usually we use it just stable voltage. You understand what I'm saying? Because these 2 circuits, this circuit and this circuit, are separated. You get what I'm saying? So if there is something happening here, it's not going to impact this circuit. Because they are not electrically connected. That's what I want to say. Okay? Anyway. Now, before I move forward, guys, you understand, again, the purpose of what I'm teaching right now, you should understand what is the difference between what I did so far in inductors and what I'm going to teach now, how the situation is different. What I did so far in inductor, we had a point, and in this point we have one wire, this way. Okay? And the voltage was equal L di by dt. Voltage also equal N d phi by dt. Okay, so that's what we did here so far. But now, because these equations are not going to be valid anymore in case of coupled inductors. So why? I'm going to tell you why. So here in case of coupled inductors, we need to modify this equation to be more accurate. Okay? So actually what happens here, because because this circuit here, whatever your circuit here is, okay, because we have here current in this circuit, we have current here in this circuit, and also this circuit will have some current also in this circuit. So actually what happens here, that's why I'm gonna change this equation as you will see right now. So what happens here, this inductor will have some impact on this one because they share the magnetic pole. Okay, so and this magnetic pole, there is a magnetic field in this pole here. So what happens here, this one has impact on this one. Also, this one is going to have impact also on this one, because the current flowing here is going to change or have some impact on the magnetic field here. This is the new part we didn't have in this equation. So that's why I'm going to change this equation to consider this part. The impact of one inductor on the other. Okay, so let me show you. Okay, so here, if you have here V1, you have here L1, I have here V2, and you have here L2. Okay, and also I'm gonna define something new. I'm gonna call it M. M is like an inductance. This inductance is actually the impact of one inductor on the other. Okay, because again we share the same magnetic field. Okay, so so that's why you will see I'm going to change this equation now. I'm going to say V1 equal L di1 by dt. Okay, it's the same this one. Yes. Okay, it's the same. Plus or minus, I'm going to talk about this one. Okay, so this one here is the same like the old one. Okay, so the voltage V1 equal L di1 by dt. Plus or minus the impact of this one, 0.2 on this one. And this impact means there should be a voltage. There is a voltage induced because of the current here on this one here. And it can be plus or minus because it depends on the direction, the polarity of the voltage. The polarity of voltage can be similar to this one or it can be different. That's why plus or minus. I'm going to tell you when it can be plus or minus or how. That's the difference issue. Okay? So here should be M, which is the mutual inductance, which is actually this one actually reflected the impact. Anything between the two, should have M, and then you have I2 divided by dt. Okay, so again, this is the old one we have. Voltage across an inductor equal L di by dt. That's the old one we have. And then I'm going to add new term here. This term here is actually the impact of the second one on this one. And this impact can be positive or negative. Because this one also is going to make a magnetic field. And this impact here, I'm going to use M instead of L. So here M is actually mutual between two. Okay? The impact of this one on this one, or the impact of one inductor on the other. Okay? Same thing when I talk about V2. So V2 is actually equal here L1, here L2, di2 divided by dt. Okay, so this one exactly similar to this one. Okay, this is, by the way, L1 we call it self-inductance. Self-inductance. This one is self-inductance, but this one is mutual. Mutual means between the two. Same thing, plus or minus M di1 divided by dt. Remember, look here. That's why here we have one. Here V2, but here I have I1 because this is the impact of the other one. Same thing. In case of V1, here I have I2 because this is the impact of the other one. Okay? That's why I can say in this scenario or in this case, I can model. I liked it. I found it in the textbook. I put it in the slide. I liked it. So I can model the inductor L1 as an inductor, normal inductor L1, just a model. I can model it this way. And then I have a dependent source. So here I can model this inductor. It is like the old L1, like the inductor we had before, plus or minus this voltage, which is actually dependent source. You get what I'm saying? So because this part is similar to what we had before. So I can model this the coil here as an inductor similar to the one we had before, plus here a voltage, dependent voltage, but this voltage is coming from the other part. Okay? Same thing here. I can model this one like L2. Also here I can have also plus. It depends on what direction it is, but here this part is coming from M di1 plus divided by dt. Okay, coming from the other side. Any question, guys? Okay, so let me summarize what I said before I proceed, guys. Number one, we already familiar with inductors. Okay, we have been using inductors for several weeks now. Number one, we know what is inductors. We know it. Now, I'm explaining a new device. This device, we call it coupled inductors. Coupled. Okay? Or transformer or coupled inductor. By the way, before I move, sometimes coupled inductor can be, sometimes you have, for example, I have a coil this way, I have a coil this way, and maybe I'm going to have multiple coils. You got what I'm saying? Sometimes you can have multiple. In this case, between every two, you should have M. This is going to be more complicated. You got what I'm saying? So here you have L di by dt, this one, but this one is going to have impact. This one is going to impact. This one, but anyway, it's a too complex situation. We're not going to do this. Okay. But anyway, so here now I explained. You need what you should understand, guys. What is the difference between inductors I used before and between coupled inductor? How it is different? Okay. So it's simple. It's actually two or more coils. They are sharing the same magnetic core. They are sharing, and because also this is one thing you should understand. The second thing you should understand, it's about of coupling. It's magnetically we couple them. How by doing that? How I connected two circuits together, but not electrically. I connected them using magnetic field. That means any change in this, in one circuit, can have impact on the other one. Also, you should understand, in this case, the voltage will not be only this voltage, because if this is isolated, only one, if it's just one inductor, it's not coupled inductor, just a single inductor this way, yes, I would have only this one. But here I have one part here, okay, which is actually the induced, this you can see this one like induced voltage. Induced voltage because of the impact of the other one. It can be positive or negative. It depends on the polarity. This one helping this one or it's have different polarity than this one. Okay. Same thing for this one here. Okay. Any questions? Okay. So as you will see right now, regarding is that positive or negative, it's actually depends on the direction of the winding here. If you tell me this way and the other one which direction, you will see now in the example. So based on the direction of the winding here, or the winding here, you can actually tell if it's positive or negative as I will show in the example. Okay. So let me go to the slides here. Okay. So here I told you about it. Okay. So just, yeah, we are familiar with this one. V equals to LdI by dt. We're familiar with this one. Now we can also use this one. It's the same. Also the voltage here is actually N times d phi by dt. Okay. Phi is actually the number of flux lines. Okay, which is actually related to the magnetic field. How strong is the magnetic field you have? And actually here phi is actually CNI. C is a constant number. It depends on the geometry, constant number times N times I. That's why you can see here N d phi by dt, and phi is actually C, which is a constant number. N is the number of turns, which is constant, I of t. Okay, so here, so that means it's also the voltage should equal N d phi by dt, also should equal Cn squared because you have constant di by dt, and because it's also equal N di by dt. Now I can say L is equal Cn squared. Okay, anyway, L is equal to Cn squared. C is constant, N is the number of turns, okay? Yeah, the second one here, you can see L1 equal constant 1, N1 squared, L2 equal C2, N2 squared, okay? And then we have something, as I told you, we call it M, mutual inductance, okay? This is still inductance of winding 1 and winding 2, okay? This one is mutual. This is the impact of one with the other one. And actually, this M, there is a relation. So what is the value of M and L1 and L2? So you can see here, M is actually equal K is 2 root of L1 times L2. So it's related to L1, L2 as well. And this is M. And actually, K is a constant, and this constant we call it coupling coefficient. Okay? So if it is 1, it means a perfect coupling. Perfect couple. Okay. Yeah, that's what I told you guys. Voltage 1 should equal L1 di1 divided by plus or minus is the impact of the other one. V2 L2 di2 divided by 2d, and then the impact of the other one here. Okay. Now let's come to the point I told you about the polarity, is that positive or negative? Okay. So actually it depends on how the direction of the wire. So if you see here, guys, here this is the direction is similar to this direction. Okay, this is the primary coil. Both of them are in the same direction. But if you look here, compare this one with this one, you will find the direction is different. If you look at this one here, we do this way. Okay, but for this one, the other way. This was the direction. Okay, so because the direction is different, look at the voltage here. This is the positive and this is negative. This is the positive here is negative here. So, okay, so again, how this induced voltage can be positive or negative, again, it depends on the wiring, the direction of the wiring, okay, let's see here. If I do this way, okay, or the other way, this one will be positive. And anyway, we use the convention of dot. So we use dot here just to tell you which. So as you see here, when I put dot here, that means this is a positive. When I put dot here, that's a positive. Okay, guys. So again, so that's why you will see the circuit. So we'll put a dot here. So this dot should tell you what is the positive side. Got what I'm saying? So here, this positive side means the current will enter from here. The current will enter from here. Okay. So that means this is a positive side here and positive side here. This is the last part here I want to show you here, guys. As I told you, I can model this primary coil here as an inductor, similar to what we had before, plus a dependent source. The other one here, I can model it like a voltage source, dependent voltage source, plus an inductor. Okay. Any questions? Anyway, so next time I will teach you again. Let me just quickly tell you what I will do in the future. We already studied. We studied. If you have a normal inductor, okay, I will put it inductor. Okay. If you have an inductor, how can you analyze the circuit? We already have done it. Okay. Now, next time I will teach. If your circuit has a coupled inductor, how can you analyze it? You got it. You will see it's almost the same thing, but we have to consider now V is not equal to, because that's the main difference. What we did before, V equal LdI by dt. Now, no, I have to consider this part as well. That's the only difference. Everything else also will be almost like this. Okay, thanks, man.